In this last video on the complex numbers playlist, we are still talking about advanced problem solving. Previously, we've considered Olympiad, complex number problems. Then later we saw proof-based complex number problems. Now we're looking at multi-step complex number problems. Uh, Problems that will require you to take more than one step. Of course, we've seen such problems before. We just want to drive it home in this last video, except something else comes up. I might have to make maybe an extra video if I find something I feel is important that I should talk about. Okay, so multi-step complex number problems. Of course, you need to know the foundations, right? A complex number is written as z equals a plus bi, and a is a real part and b is imaginary part. I squared is minus 1. And we have basic operations on complex numbers, which I already talked about in initial videos, the first set of videos. We can do addition. You have a plus bi plus c plus di. Then, so what you do here is collect the real parts without I. That's a and a plus c. The parts with I, you have b plus d I. That is the imaginary part. And then you can also multiply. So you do multiplication. Of course, here bd I squared. I squared is minus 1. So this would have been minus bd. Then every other thing, then you can then say AC minus BD plus AD plus BC multiplied by I altogether. And then the conjugate of Z itself, which is Z bar, is A minus BI. And the modulus of Z, interestingly, same as modulus of Z bar, will be square root of A squared plus B squared, as you've seen previously. And then we have strategy for multi-step problems. Usually, you want to simplify the algebra first. Then you convert forms if needed. We need to convert from rectangular to polar to exponential, or back to from exponential to polar, or from polar to rectangular. You can do that back and forth. Then you can use identities carefully. Then you can multiply by conjugates for division, and you can separate real and imaginary parts at the end. So example one, I mean, these are regular things we have come across already. So this is just like a kind of overview before we we bring it to a close. So example one now, you have 2 plus 3i into 1 minus 4i all over 3 plus 2i. So first, you need to simplify this. You can first expand the numerator. So you have 2 plus 3i into 1 minus 4i. That's, 2 minus 8i plus 3i minus 12i squared. That's 2 times 1, 2. 2 times minus 4i, that's minus 8i. 3i times I, that's 3i. Then 3i times minus 4i, that's minus 12i squared. And so since I squared is minus 1, you then have 2. You can add this up. So you have 2 minus 8i plus 3, that's minus 5i. Then minus times minus 1, 12 times 12. That's 2 minus 5i plus 12. That's 2 plus 12, 14. You have 14 minus 5i. Then you can multiply by the conjugate now. Now you see why it's multi-step now. So you have you have taken care of the top. So you have 14 minus 5i over 3 plus 2i. Then to multiply by the conjugate of the numerator, I mean denominator. So the denominator is 3 plus 2i. The conjugate is 3 minus 2i. Uh, so you multiply by 3 minus 2i over 3 minus 2i, just like you're multiplying by 1. So it doesn't change. It will change the form, but it does not change the essence of the expression. So what we then do is, of course, we expand as usual. So 14 minus 5i into 3 minus 2i. So 14 times 3, 42. 14 times minus 2i, that's minus 28i. Minus 5i times 3, that's minus 5i. Then minus 5i plus 2i, that's plus 10i squared. So you have 4i minus 43i minus 10, and that is 32 minus 43i. So you then compute the denominator. The denominator is difference of two squared easily. That's difference of two squares. That's 3 minus 2i squared. That'll be 3 squared is 9. That's 3 squared minus 2i squared. That's 3 squared is 9. 2i squared is that'll be minus 4i squared. And I squared is minus. So minus minus is 4. 9 plus 4, 13. So finally you have 32 minus 43i over 13. That's 32 over 13 minus 43 over 13i. So you have to do a couple of steps. It's not like you have a problem, you just rationalize and go. So no, here you have to first of all tidy up the numerator before you then rationalize. So of course, We can also do symbolic Python here to see if our answer is right. And this is what exactly has happened right here. And we get the same 32 over 13 minus 43 over 13i. Example 2 now. We've come across this before. We have 1 plus I raised by 5. So you want to convert to polar form first because it's easier, or even exponential form, right? And what do? You just look for R. So if you look for R is the magnitude of Z. If Z is I plus 1, so the magnitude of that will be square root of 1 squared plus 1 squared, which is square root of 2. That is our R here. And then you need this pi over 4, which is arctan of 1 over 1. 1 being the coefficient, y over x, right? Y being the coefficient of I, that's 1. X being the constant, the real part, which is also 1. So arctan of 1 over 1 is arctan of 1, which is 45 degrees, or pi over 4 in radians. So I plus 1 then becomes root 2 into cos pi over 4 plus I sine pi over 4. And then using the Moivre's theorem, which simply tells us that the power, if you raise any complex number to power n, it's the same thing as r raised to power n, the number part raised to power n, and then the angle part multiplied by n simply. So you then have 1 plus I raised to power 5 to be root 5 raised to power 4, root 2 raised to power 5 cos 5 pi over 4 plus I sine 5 pi over 2. So, and if you tidy that up, so this is 4 root 2, because this is going to be um you know this is 2 root 2 in 5 places. That's root 2 raised to power 4 is already root 2 raised to power 4 is 2 raised to power half times 4. That is 2 raised to power 2, which is 4. And then you still have 1 root 2 left. That's 4 root 2. And for this time, you have 5 pi over 4. You have minus root 2 over 2. And then minus I root 2 over 2. And then by the time you tidy up all of this, multiply all this out, you have minus 4 I, like that. So if you are going to do it algebraically to be messier than this, of course, power 5 is still easy. You may still be able to pull that off using binomial expansion. But polar form and the Merge theorem, it makes everything pretty easy. So you want to confirm that it has 1 plus 1j raised to power 5, and you get 4 minus 4 minus 4j. Then you have example 3. So you want to solve z squared plus 4z plus 13 equals 0. Yeah, here it's quadratic in nature. Just use your quadratic formula. So z is minus b. So here a is the coefficient of z squared, as 1. The coefficient of z is b, that's 4. And then c is 13. So you have z equals minus b plus or minus square root of b squared minus 4ac all over 2a. So that's minus 4 plus or minus 4 squared, that's 16. Minus 4 times 1 times 13, that's 52. All over 2 times 1, that's 2 here. So you have minus 4 plus or minus 16 minus 52 is minus 36. So, and all over 2. So you have minus 4 plus or minus square root of 1. Minus 1 is I. Square root of 36 is 6. So you have minus 4 plus 6i over 2. And that means z is minus 2 plus or minus 3i. So with that in place now, we can also confirm using symbolic Python. So this gives us minus 2 minus 3i, then minus 2 plus 3i. So just like minus 2 plus or minus 3i. So we have two expressions like that. So then we have another example. Example 4. You have 3 plus 4 over 1 minus I. And we want to find the magnitude of z. So before we find the magnitude of z, we want to simplify it to the smallest level, where we just have z as a plus bi, or x plus yi, if you like. So first of all, you want to multiply by the conjugate, which is 1 plus I, because the denominator is 1 minus I. So you have 3 plus 4i into 1 plus I all over 1 minus I into 1 plus I. So yeah, if you tidied all of that up, the denominator ends up being 2, as you can see. And then that's 1 squared minus I squared, like I always like to say. That's 1 minus I squared. That's 1 minus minus 1. That's 1 plus 1, 2. And then for the top, now we have 3 times I, 3. I mean, 3 times 1, 3. 3 times I, 3i. 4i times I, 4i. 4i times I, 4i squared. 4i times 1 is 4i. 4i times I is 4i squared. So we have 3 plus 3i plus 4i, that's 7i. And then 4i squared, that's I squared is minus, so minus times 4 is minus 4. Then 3 minus 4 is minus 1 plus 7i. And then you have your z to be minus 1 plus 7i over 2. So it is easier to square this I mean, to find the magnitude of this than to find the magnitude of this. So you simplify first. That's why we are talking about multi-step. So you simplify first, then you can now take modulus. So for modulus, now you have the component minus 1 over 2 plus 7 over 2i. So absolute value of z net is now square root of minus 1 over 2 squared plus 7 over 2 squared. That means you have 1 over 4 plus 49 over 4. That's square root of 50 over 4, which is 5 root 2 all over 2, like that. And 5 root 2 over 2, if you confirm it numerically, we can also check on Google, right? Or Desmos or something. So we have 5 square root of 2 over 2. 5 times square root of 2, 5 times square root of 2 divided by 2. So that's 3.5355, blah, blah. So this is 3.535533 and all the rest. So that is correct. So for example 5 now, for example 5, we then have, we want to find all z such that absolute value of z minus 2 plus 3i is equal to 4. So of course here we let z be x plus iy. So that means you have z minus 2 plus 3i. So and if you put all of that together, you're going to have x minus 2 plus uh okay, yeah, it's more like you have x plus yi minus 2 minus 3. So that'll be x minus 2 plus y minus 3. And by the time you take the magnitude, you have x minus 2 squared plus y minus 3 squared. And of course, we know that all of that is 4. So that's 4. If you square both sides, you have x minus 2 squared plus y minus 3 squared is equals 16. So this is now a circle now. This is a circle whose center is at 2, comma 3, and the radius is square root of 16, which is 4. So the circle, the all z that satisfies this equation will be it will be the circle whose center is at 2, 3, and the radius is 4. And then of course we can also plot that kind of curve right here. Okay, we can do that here. So we do the plotting, just fix up all of that and you get that. So we have some key takeaways here. So first, always simplify step by step, then use conjugates for division, convert to polar form for powers, separate real and imaginary parts carefully, don't mix them up, and then verify results using Python when necessary. Okay, uh, verify using Python. Okay, so let's go on to the practice problems like we always have. Um, so here now we have problems 1 to 6 here. Simplify, find the conjugates and modulus. Then you have 7 to 13. And then you have 14 to you have the rest 14 to 20, like that. So as usual, I want to solve two of them. I'm solving 3 and 10. Question 3 says to compute 5 plus 2i all over 1 minus I. Of course, we just need to rationalize in that case. And question 10 says to solve z squared plus 6z plus 13 equals 0. And then you have other ones. Or maybe I should just go for question 17, which is a bit more challenging. I want to substitute 3. I'll do 3 and then I'll do 17. Let me do 2 and 17. Or better still, let me do uh okay. I guess I'm thinking about any other one that might be challenging. Okay, let me do 13 and 17. Yeah, 13 and 17. So, but I think 3 and 10 may be too simple. So let's do 13 and 17. 13 is 1 plus I cube all over 1 minus I. 1 plus I cube all over 1 minus I. So problem 13. Problem 13. Evaluate 1 plus I cube all over 1 minus I. Did I get that right? Let me confirm for the last time. 1 plus I raised to power 3 all over 1 minus I. Okay, so with that done, so to evaluate that, so we have 1 plus I raised to power 3 all over 1 minus I. Well, we need to simplify the top first. So, and for 1 plus I, we can use binomial expansion, and that's like we say we start with we have 1 raised power 3, I raised power 0, like that. Then plus the coefficient, of course, if you use Pascal's triangle, that's 1 when something is raised power 0, when it's raised power 1, 1, 1, when it's raised power 2, 1, 2, 1, when it's raised power 3, we have 1, 3, 3, 1. So that means we have so that's why we have 1 first here, then 1 raised power 3, I raised power 0, plus the next thing is 3. So I raised power 2, 1 raised power 2, I raised power 1. Okay. The next we have 3. This next 3 now. 1 raised power 1 raised power 1, I raised to power 2. And lastly, we have this one. So we have 1 into 1 raised power 0, 1 raised power 0, I raised power 3. All of this now, all over 1 minus I. Okay, so we have that expansion. Or we could have made it, do we need to take it to polar form? I don't think, yeah, we could make it polar form. Maybe I'll do polar form too. But let's just go ahead with this first. So this is all this is 1. So I raised power 0. Everything here is 1 in short. That's 1 times, this is 1 times 1. I raised power 0 is also 1. Then plus 3. 1 squared is 1. I remains I. Then plus 3. 1 raised power 1 is 1. I squared is minus 1. This I squared here is minus 1. Plus 1. 1 raised power 0 is also 1. I raised power 3 is minus I. Because I raised power 3 is I squared times I. The I squared is minus 1. Then times I. Then all over 1 minus I. Okay, so then we have 1 plus 3i minus 3, you know, 3i minus 3, then minus I again, all over 1 minus I. So we have, we can tidy things up. 1 minus 3 is minus 2, then 3i minus I, that's plus 2i, all over 1 minus I. Um, can I see any pattern here? Okay, I think there's a pattern. Can we factorize? When I factorize this, I have minus 2 into 1 minus I. Yeah? So that's minus 2 plus 2i all over 1 minus I. So this can easily cancel out, and we have minus 2. Okay, so let's do polar form, which I think which may be overkill, by the way, but let's try it and see what happens. So let's do that's method 1 right there. This is method 1. Doing method 1, that's direct algebra. So method 2 now, method 2. So at least that will help us confirm if you are correct or not. So we have 1 plus I raised power 3 all over 1 minus I. Okay, so in I even like exponential form. In exponential form, if let's say we have z1 to be 1 plus I, that is absolute value of z1, which is square root of 1 squared plus 1 squared, being the constant and coefficient. So that's square root of 2 easily. And then for theta, theta is arctan of 1 over 1, which is pi over 4, like we already know it. So that tells us that z1 is equal to 1 plus I, and that is equal to, generally we know polar form is z1 equals, um, if you like, r1 raised power e raised power I theta. So that's what z1 will be, or let's say theta 1. So here now we have r1, then this is theta 1. So that means z1 is root 2 e raised to power root 2 e raised power I pi over 4. I guess it's too close. So Z1 now is R1 e raised power I theta 1, and that is root 2 e raised power I pi over 4. So we have that first. So for the second one, we have I minus 1. So for, let's say, Z2, which is I minus 1 minus I, right? This I and 1 thing. Okay, 1 minus I. So this is 1 minus I. So that's 1 minus I. So again, we need R2, which is, of course, we need to write that as Z2 equals R2 e raised to power I theta 2. Okay, so R2 is magnitude of Z2, which is magnitude of 1 squared plus minus 1 squared. That is square root of 2 down. And then we have theta. Theta is arctan of minus 1 over 1. So, and that is arctan of minus 1. And that is without, that should be minus pi over 4, I believe. Let's see. Arctan of minus 1. So, arctan of minus 1. I think that should be minus pi over 4. In radians for sure. That's minus pi over 4, yeah? So, we have minus pi over 4. So this is minus pi over 4. So then Z2 is equal to R2, R2 e raised to power I theta 2. So that's root 2 e raised to power I minus pi over 4. That's e raised to power minus I pi over 4. So we have Z2 like that. So what do we finally have? We can then go ahead and say, so 1 plus I raised to power 3 all over 1 minus I is the same thing as 1 plus I is root 2 e raised to power I pi over 4 raised to power 3 all over root 2 e raised to power minus I pi over 4. So we go carefully now. So this is root 2 raised to power 3, and then this is e raised to power I 3 pi over 4. That's I pi over 4 times 3. That's 3 pi over 4 all over root 2 e raised to power minus I pi over 4, like that. So it's like this is even longer than what I did before, but it's okay. So here now we have root 2 raised to power 3. Okay, I mean, we can say this is what I want to be. Okay, I mean, this is root 2 squared times root 2 all over root 2 on this side. Then here, e raised to power I 3 pi over 4. Then, because this is minus, we can then say times e raised to power I 3 pi I pi over 4, because the minus is gone. So we take it up. So this cancels this. So we then have root 2. Root 2 squared is 2, definitely root 2. So we then have e raised to power I pi over 4 plus I 3 pi over 4 plus I pi over 4. That is simply 4 pi over 4. So this is simply pi I. So that's e pi I. So this is 2. I believe e pi I is 1. Exponent of pi I should be 1. So let's check. Exponent of pi I. Exponent of pi times I, not 1. So exponent of pi I is minus 1. Okay, good. It's actually minus 1. Exponent of pi I is minus 1. So we have this times minus 1, and that is equal to minus 2. Exactly what we got. But it looks like the first method works better. Minus 2. I mean, it's faster actually. Then we can conclude. So 1 plus I raised to power 3 all over 1 minus I is equal to minus 2. Following the two methods, we get the same result. So let's go for, I think, the other problem I like to solve, which is a bit challenging, is problem 17. Well, I mean, not so serious, but it's okay. So 4 plus 3i, 4 minus 3i over 1 plus I squared. Okay. Problem 17. Problem 17. Evaluate 4 plus 3i into 4 minus 3i all over 1 plus I all squared. I check again. to be sure. Yeah, that works. So we move on. Okay, so I'll just take it straight. I have 4 plus 3i into 4 minus 3i all over 1 plus I all squared. So I'll just do both simultaneously. So this is 3i. So, this is 4 plus 3i, 4 minus 3i. Difference of two squares led to this. So we can have 4 squared minus 3i all squared all over. To expand this now, we know that is 1 squared plus 2 times 1 times I. That's 2 times 1 times I plus I squared. Okay? So that's expanding straight up. Like that. 4 raised to power 2 is 16. Then this is 9i squared all over. Down here we have 1 plus 2i plus I squared. Okay? And then we can move on to say this is 16 minus 9. I squared is minus 1 all over. Down here we have 1 plus 2i. Then plus I squared is a minus 1 again. So we then have 16 plus 9 all over 1 plus 2i minus 1. So that means we have 16 plus 9, that's 25, over 1 cancels 1 all over 2i. So we now rationalize. To rationalize it, it's easy. We just multiply by I over I. So that's 25 over 2i times I all over I. We don't have to do 2i because I is all that's all the discussing problem. So you have 25i over 2i squared. So that means we have 25i all over 2 into minus 1. So that means that is 25i all over minus 2. And that is equal to minus 25 over 2i. That's all that is. Or if you like, you want to take it further, you can say, you can then say that is minus 12.5i. Okay, so that leads us to the conclusion that we can then say, so 4 plus 3i into 4 minus 3i all over I plus 1, 1 plus I squared, 1 plus I all squared, 1 plus I squared is equal to minus 25 over 2i. And that is it. So with this, we come to the end of this interesting video on multi-step complex number problems under advanced problem solving under the complex numbers playlist. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If unless something comes up, this is most likely the last video on the complex numbers playlist. So see you again when I talk about another playlist or something like that. Let me know how helpful this is for you. Um, and if you'd like me to try out something else, feel very free to let me know. Don't forget to try your hands on the problems so you can see how well you understand the concepts. Um, okay, 6 to 13 here, and then the rest 14, 13 to 20. Yeah. So if you have subscribed to this channel already, I thank you very much for doing that. If you have not subscribed, why not go ahead and do that right away? And having subscribed, you can also click on the notification bell so that you can always get alerted each time a new video is released. Afterwards, you can also become a member of this channel by clicking on join. That gives you special privileges, like having to see some videos first before other people, or seeing some videos exclusively that others don't get to see because you're a member of the channel. You can request for PDF copies of my notes. You can as well hang out with me online or physically if you are ever in the same geographical location to discuss whatever interests you on my channel, be it mathematics, data analysis, data science, machine learning, scholarships, writing books, anything like that. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.